Your temperature is 39 degrees Celsius. You are the hottest you have been in years. And you are under 3 blankets, shaking hard enough that your teeth click together, completely certain that you are freezing. Both of those are true at the same moment, and the reason is stranger than the infection. Deep in your brain sits a small cluster of neurons that decides what temperature your body should be. Call it the set point. An infection did not heat you up. It made those neurons move the target from about 37 degrees to 39. Your temperature has not changed yet, so your body is now 2 degrees below where it is supposed to be, and it responds the way it would to a snowstorm. That gap is the chill. So here is how a bacterium in your lung moves a dial inside your skull. The outer wall of many bacteria is studded with a fatty sugar called lipopolysaccharide, LPS for short, and your immune cells carry a sensor shaped to recognize it on contact. A macrophage, one of the large immune cells patrolling your tissue, binds it and starts shouting chemically, releasing interleukin-1, interleukin-6, and tumor necrosis factor. Cytokines, short protein messages, spilling straight into your blood. And then they hit a wall. Your brain is wrapped in the blood-brain barrier, vessels whose lining cells are sealed edge to edge so tightly that most large molecules in your blood never get through. So the message gets rebuilt on the far side. The cytokines dock onto receptors on the endothelial cells lining your brain's own vessels, and those cells switch on 2 enzymes, COX-2 and MPGES1, which build a small fatty molecule called prostaglandin E2 and release it on the brain side of the wall. What reaches your thermostat is a molecule manufactured by the wall itself, carrying the same message. Prostaglandin E2 drifts a short distance and lands on a receptor called EP3 on neurons in the median preoptic nucleus, a patch of hypothalamus about the size of a grain of rice sitting behind your eyes. Those neurons hold your temperature down all day. They fire constantly, and their firing suppresses the circuits that generate and conserve heat, like a foot resting on a brake. Prostaglandin E2 quiets them. The foot lifts, and the target rises. Now watch your body chase it. Nerves clamp down the small arteries feeding your hands, feet, ears, and nose, and warm blood is pulled back toward your core, which is why someone with a raging fever has cold, pale fingers. Tiny muscles at the base of each hair contract, which is gooseflesh. Your skeletal muscle starts contracting in fast, alternating bursts that do no useful work at all. That is shivering, and the waste is the point. Nearly all of that energy comes out as heat. Around your collarbones sits brown fat, a tissue whose mitochondria burn fuel purely to make heat, and the same nerves light it up. And you pull the blankets tighter because your brain is telling you something accurate. You are colder than you are supposed to be. Over the next hour or two, the actual temperature climbs until it meets the set point. The moment the gap closes, the shivering stops and the sensation flips. Same body, same infection, same reading on the thermometer, and now you feel hot. The climb does not run away with you either. As the fever builds, your brain releases its own restraining signals, vasopressin, alpha-MSH, and stress hormones like cortisol. And that is much of why ordinary infectious fevers stay under about 41 degrees Celsius, a little under 106 Fahrenheit. And a fever breaking is the same graph in reverse. The infection clears, prostaglandin production stops, the brake comes back on, and the set point drops to 37, while your temperature is still 39. Now you are 2 degrees too hot. Every vessel in your skin opens and you sweat through the sheets. That soaking is the dial moving back, seen from the inside. It is also what a fever medicine does. Aspirin and ibuprofen block the COX enzymes, so less prostaglandin E2 gets built, and paracetamol works centrally by a route that is still less settled. None of them carry heat out of your body. They lower the target, and your body does the cooling. So, how confident is anyone that this cluster is really the dial? In 2025, a team reported that in mice, they could work it from both directions. They shut those EP3 neurons down, and the mice ran a fever with no infection anywhere in the animal. They activated the same cells, and body temperature fell and stayed down into a torpor-like state. This is mouse work, and nobody has a switch for a human fever, but the cluster your own prostaglandin E2 silences is a real two-way control, and the effect outlasts the trigger, sometimes for hours. Which leaves the real question: why would a body build any of this? Fever is old, older than warm blood. Infect a desert iguana with bacteria, put it in a chamber where one end is hot and the other cool, and it walks to the hot end and holds there, running a couple of degrees above normal. Fish do the same by swimming into warmer water, and animals denied the warm end die more often. One measured reason: at fever range temperature, a heat shock protein called HSP90 gathers a T cell's adhesion molecules into sticky clusters, so the cell grips the vessel wall harder and gets into infected tissue faster. A few degrees up, your immune cells are physically better at their job. It is not free either. Every degree Celsius of fever costs roughly a tenth more metabolism, and part of why you feel wrecked is simply that bill. Whether lowering a fever changes how an illness turns out is genuinely unsettled. One large trial in intensive care brought patients' temperatures down with paracetamol and found no difference in survival. Heat clearly helps immune machinery in the laboratory, and the clinical question stays open. This is an explanation of a machine, not health advice, and anything you are actually worried about belongs with a doctor. Two last things people get wrong. Fever and heat stroke both put a big number on a thermometer, and inside the body, they are opposites. In a fever, the set point moves up, and your body cooperates. It stops when it arrives. In heat stroke, the set point never moved. You are being heated from outside, or by your own working muscles, faster than you can shed it, and the body is still trying to cool the whole time, sweating, skin vessels wide open, losing anyway. That is why fever medicine does nothing for heat stroke. There is no raised target to lower, and the heat has to be taken out physically. And the number in your head is probably wrong. 98.6 Fahrenheit traces back to one German physician in the 1850s who took around 1 million readings and published the average. Modern data sets put the adult average lower, nearer 36.6, and it has been drifting down for over a century, while your own swings about half a degree between early morning and late afternoon. There is no universal normal. There is yours at this hour, measured this way. And an ordinary infectious fever does not cook your brain. The temperatures that damage tissue sit above where your own brake holds a fever. And febrile seizures in small children, frightening as they are, generally do not cause brain damage. So the next time you are shaking under a pile of blankets, that is not your body losing control of itself. Somewhere behind your eyes, a few thousand neurons have been told there is a bacterium in your blood, and they have moved the number they defend. The shivering is you climbing toward it.